This is Mathematical Models and Numerical Methods involving first-order differential equations, and in this video we are going to be talking about electrical circuits. So let's take a look at a simple electrical circuit. So here what we have is an RL circuit, and here we have an RC circuit. So basically we have some sort of voltage source. So let me go ahead and put a little star there. So in this simple electrical circuit, we have to have some sort of a voltage source. And that might be maybe a battery or a generator that would provide that source. Now, in the RL circuit, you can see, and in the RC circuit, you can see that we have a resistor. And then in these circuits, you have either an inductor or a capacitor. And let me move this here. Let's go ahead and put that green star there by the inductor where we will have a voltage drop. And this constant L is called an inductance. And that's a constant, proportionality constant. And then, of course, we also have the constant C, which represents capacitance. It's also a constant. So here we have our RL circuit and our RC circuit. And I'll just go ahead and highlight those. Okay, so let's take a look at how we are going to define that voltage drop across the capacitor and across the inductor. And then we will also take a look at the current passing through the resistor. So if we would apply Kirchhoff's voltage law, let's begin with the RL circuit. And here we can see, using Kirchhoff's law, we can see here that this E of T is going to be the voltage, and that voltage that's supplied to the circuit. And then taking a look at E sub L, here we have the voltage drop across that inductor. And then here we have E sub R, and that is going to be the voltage drop across the resistor. Okay, so looking at each one of these voltage drops, let's begin with E sub L, and here E sub L is equal to L multiplied by di dt. And that is using Faraday's law and Lenz's law that the voltage drop, E sub L, across an inductor is proportional to the instantaneous rate of change of the current. And now looking at E sub R, we see that the voltage drop E sub R across a resistor is proportional to the current I passing through that resistor. So that is our voltage drop across the resistor. Okay. We note that this equation is linear. And we can come up with our integrating factor. And I will leave this to you to come up with a formula for I sub t. So this solution gives us the amount of current at any time t. So I want to make it a point that this is our differential equation, and this is our solution to that differential equation. Now, let's go ahead and take a look at our RC circuit. Here we have the voltage drop. I'm going to go ahead and write that on the top. Across the capacitor, and then we of course have E sub R, which is our voltage drop across the resistor, just as we had in the RL circuit. And then of course we have our voltage supplied to the circuit. And that's at any time t. So now we are going to go ahead and derive this solution. Okay, so the first thing we want to look at is that E sub c is equal to 1 divided by c multiplied by q. And this is that the voltage drop across the capacitor is proportional to the electric charge Q on the capacitor. So that's that electric charge on that capacitor. Okay, so now we have 1 divided by C multiplied by Q plus, and again we have that E sub R is our voltage drop across the resistor, and that is proportional to the current I passing through that resistor. So we'll use RI, and then we still have that's equal to E of t. So now let's go ahead and write this as Q divided by C plus R multiplied by dq dt. And here we know that the capacitor current is the rate of change of its charge. So it is the rate of change of its charge. And we will go ahead and let this E of t equal our voltage, since our voltage is a constant. And we also want to make sure we know that I is equal to dq dt. Okay, so let's keep going, and we'll go ahead and solve this. This is a separable. So this is a separable DE. It's also linear, and it can be solved. But let's go ahead and use separation of variables. So moving the Q over C to the other side, we have R dQ dt is equal to V minus Q over C. And now we come up with dQ dt is equal to V minus Q divided by C divided by R. And of course, we have a complex fraction there. Let's go ahead and clear that. Multiplying the numerator and denominator by C, we have CV minus a Q divided by RC. Okay, so now we'll begin to separate our variables so that we can integrate. So now we have 1 divided by CV minus Q. And we'll keep the dq over there. And then we have 1 over RC dt. So we separate, and now we will integrate. And now we have the opposite of the natural log of CV minus Q is equal to T over RC plus a constant. And we'll go ahead and use K since we've already used C in our equation. And so now let's go ahead and multiply both sides by a negative. And that's still a constant. And then we have CV minus Q is equal to that constant e to the negative t over RC. And we are getting there. That's the opposite of Q is equal to KE to the negative T over RC minus CV. And we finally come up with Q of T is equal to that constant E to the negative T over RC plus CV. And that is our solution. I'm going to move that down just so we kind of keep that separated, and we definitely have the solution to our differential equation. And this is our capacitor charge at any time t. Okay, let's go ahead and work our first example, but let's keep in mind that this is our solution to our separable DE. And that's for our RC circuit. And we will be using this solution, I of t, for our RL circuit. And that gives us the current at any time t. Okay, so let's see what we have for our first example. An industrial electromagnet can be modeled as an RL circuit while it is being energized with a voltage source. If the inductance is henries, and let's highlight that, and the wire windings contain 3 ohms of resistance, how long, and let's highlight that, how long does it take a constant applied voltage to energize the electromagnet to within 90% of its final value? And of course, that's when what we're looking for is when the current equals 90% of its asymptotic value. So let's go ahead. We have an RL circuit here. And let's go ahead and write our equation. L di dt plus Ri is equal to E of t. And of course, we're going to be using our given solution to that differential equation. And we have I of t is equal to E to the negative RT over L multiplied by the integral of E to the RT over L times E of t over L dt plus that constant K. Now keep in mind, we were given that the resistance was 3 ohms, the inductance was 10 henries, and of course, that voltage was constant, so we'll go ahead and let E of t equal V, okay? So let's go ahead and plug that in. We have I of t is equal to E to the negative 3t over 10 multiplied by the integral E to the 3t over 10 times V over 10 dt plus K. Let's go ahead and evaluate that integral. We have e to the negative 3t over 10. And here we have v over 3 e to the 3t over 10 plus k. Let's go ahead and do some simplifying by distributing that exponential term. So here we have v over 3 plus k e to the negative 3t over k. Now, since the initial current is 0, we now have 0 equals v over 3 plus k. Of course, t is equal to 0. So we have k equal to the opposite of v over 3. And therefore, I of t is equal to v over 3 minus v over 3 e to the negative 3t over 10. Now we want to find that limiting value. So let's go ahead and take a look. So we want to find the limiting value of our current I, and that's going to be I sub infinity, okay? So going ahead and doing that, I sub infinity is the limit as t approaches infinity of I of t, which is the limit as t approaches infinity of v over 3, and I'm going to go ahead and factor that v over 3 out, 1 minus e to the negative 3t over 10. And of course you can see as t approaches infinity, that is simply equal to v over 3. And so now let me go ahead and just put that there. That is our limiting value of our current. And so now we need to find t when I of t is equal to 0.9 times that limiting value. Okay? And that's going to be 0.9 times v over 3. So let's go ahead and do that. And I am going to need to make all of this a little bit smaller. And it's okay because I can use that next line. So we have 0.9 times v over 3 is equal to v over 3 times 1 minus e to the negative 3t over 10. So we have e to the negative 3t over 10 is equal to 0.1. And then I'll just go ahead and write here. We come up with t is approximately the opposite of 10 times the natural log of 0.1 divided by 3, and that's approximately 7.68 seconds. So it takes 7.68 seconds to energize the electromagnet to within 90% of its final value, of that limiting value. Okay, let's take a look at our next example. A 10 to the negative 8th farad capacitor, and of course that's going to be 10 nanofarads, is charged to 50 volts and then disconnected. One can model the charge leak age of the capacitor with an RC circuit with no voltage source. So we have no voltage source and the resistance of the air between the capacitor plates. On a cold, dry day, the resistance of the air gap is 5 times 10 to the 13th power ohms. So that's for our cold day. And on a humid day, the resistance is 7 times 10 to the 6th power ohms. How long will it take the capacitor voltage to dissipate to half of its original value on each day? Okay, so let's go ahead and write this down on our cold day. Well, we have it highlighted up there. I won't write that. We're able to find those, each one of those, and we will work these separately. So let's go ahead and write our equation for our voltage of our RC circuit. And we take a look at that differential equation that we used Kirchhoff's voltage law, and we came up with E of T is equal to Ri plus Q over C. And then we said that the capacitor current is the rate of change of its charge. So we will go ahead and replace I with dq dt, and then we have plus Q over C. Now we are going to go ahead and let E of T equals V, and we solve this a separable dE. So here we have a separable dE, and we will be using that solution that we derived. So we have Q of T is equal to KE to the negative T over RC plus CV. So I want to make a note that we are going to ignore C times V. We're going to treat it as unknown. It will make things a lot easier. So now we have that the voltage drop across the capacitor is equal to Q of T divided by C, and that's equal to, move this over here, and that's equal to K E to the negative T over RC, which we have above, divided by C. So we have the voltage drop across that capacitor at any time t is equal to, and let's call this a new constant, K sub 1 E to the negative T over RC. And here we have K1 is K divided by C. And since that initial charge on the capacitor is equal to 50 volts, we can say that 50 is equal to K sub 1, since of course that would have T equal to 0. And go ahead and write that in purple. And therefore, we have E sub C at any time t is equal to 50 E to the negative T over RC. So here we have an equation for our voltage drop across the capacitor at any time t. So now let's go ahead and use E sub C of T equal to 25. Since we were asked how long it will take the capacitor voltage to dissipate to half of its original value. And we'll go ahead and use C as 10 to the negative 8th, our capacitor. Okay, so now let's take a look at our cold day, a cold, dry day. So for a cold day, we're going to have R equal to 5 times 10 to the 13th ohms. And that's the resistance of the air gap. And so now we will go ahead and plug that in here to this equation. Okay, and so we have 25 is equal to 50 e to the negative t over RC. And actually we can use that for both of our days. So we will go ahead and use that right here. And we'll go ahead and plug that RC in there. And then we can use that for both of those days. So the opposite of t over 10 to the negative 8th multiplied by R. I'll go ahead and put R in parentheses. Okay, so now since we're going to use on our cold day that value for R, we have 25 is equal to 50 e to the negative t divided by 5 times 10 to the 13th, and of course times 10 to the negative 8th. I'm going to go ahead and bring that 50 times, yeah. Okay, and then we end up with 1/2 equals e to the negative t over 5, times 10 to the 5th power. And we end up with the natural log of 1/2 is equal to the opposite of t over 5 times 10 to the 5th. And I came up with t is equal to negative 5 times 10 to the 5th power multiplied by ln of 1/2. And you get approximately 346,573.6 seconds. And I went and just converted that to hours. That's approximately 96.27 hours. Okay, let's go to a humid day. And on our humid day, the resistance is given to be 7 times 10 to the 6th ohms. And we're going to go ahead and plug it into that same equation. So we have 25 equals 50 times e to the negative t divided by 7 times 10 to the 6th times 10 to the negative 8th. That does not look good, so I'm going to bring this down so I can get that exponent a little bit better. The opposite of t divided by 7 times 10 to the 6th. And then we still have that 10 to the negative 8th there in the denominator. And we come up with 1/2 is equal to e to the negative t divided by 7 times 10 to the negative 2 power. We have the natural log of 1/2. Continuing in that same fashion, and I came up with t to be equal to negative 7 times 10 to the negative 2nd power multiplied by the natural log of 1/2, and that's approximately 0.0485 seconds. So quite different on a humid day as opposed to a cold day, as how long it will take the capacitor voltage to dissipate to half of what it started with. And that concludes this video.